What's up guys, it's Simon Fiaz and today's video is on AQA Level Chemistry 2017 paper 2. Question 1. Draw the displayed formula of compound J. And compound J, so I'm going to go the opposite. No, I'm sorry, compound J, sodium hydroxide aqueous. It's a halogen alkane. It's obviously going to be nucleophilic substitution. So all I'm going to be doing, is replacing this with the OH group. So it's going to be CH3, CH2. Remember displayed formula, CH2, OH. And don't just do OH, do O and then that's your H. Name the mechanism for reaction 2 and give it a central condition. I'm reacting with ammonia and a formula name mean it is nucleophilic substitution. Nucleophilic substitution. I'm recording. Yeah, I'm recording. The condition excess ammonia. Excess NH3. And this is all year 1 content. And then 1.3, a mass question. Calculate mass of this produced from this much of Br, assuming 75% yield. Calculate the mass of this produced from this much of this Br. So first thing I would always do is calculate the moles. I can quite easily find out the moles of this by just doing the mass over the MR. 1 to 2.9. I feel like most students would get to that point, right? Then the second step is identifying, well, they both got a 1-to-1 molar ratio, right? So the moles of CH3, CH2, CH2, NH2 is the same, right? Therefore, I can now find out the mass of this because moles is mass over MR. Mass is going to be the moles, which is going to be 0.205 times by the MR of CH3, CH2, CH2, NH2, which is 59. Then I'm told, assuming 75% yield, then I just times by 0.75. And you get 9.07 grams. It must be to two decimal. Must be to three significant figures. I don't know why it keeps doing that. Anyway, when reaction 2 is carried out under different conditions of compound with molecular formula, this is produced through the skeletal formula of a compound. So, should just look something like, yeah, 1, 2, 3, 4, 5, 6, 7, 8. 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. And obviously your N group. Identify the functional group in the compound including its classification. Tertiary amine. Tertiary amine. Identify the region and conditions using reaction 3. In reaction 3, I'm going from a halogen alkane to an alkene because C3H6. So what conditions are that? Halogen alkane to alkene, potassium hydroxide reflux and ethanol. Potassium hydroxide and ethanol. Don't really need to reflux, I guess. And this is just how well you know the organic synthesis route. If you don't know it, you're gonna struggle with these type of 1-2 markers, and that's the game. You have to memorize that synthesis route. Name and outline the mechanism for reaction 3. Yeah, halogen alkane to alkene. It's obviously going to be electrophilic addition. No, it's not. Halogene alkane to alkene. Fraction 3. Halogene alkane to alkene. No, it's going to be elimination. If it was, what's it called? If it was, yeah, electrophilic addition is alkene to yeah, so it's going to be elimination. It's a simple mistake on my end. Elimination. 4 marks for this, so I definitely don't want to get it wrong. So CH3, CH2, CH2Br. Let's draw that out. CH3, CH2, CH2Br. Fill in the hydrogens, right? CH2, CH2Br. And remember, with elimination, lone pair of electrons, OH minus ions acts as a base, takes a proton, left carbon has a spare electron, wants to form a double bond, order for it to form. No, it won't work in this case because I'm not. So I need to do it another way. So what I have to do instead is forget this. The lone pair of electrons, OH minus, takes a proton from here. Left carbon has a spare electron, wants to form a double bond. CBr bond must break. And then what you're left with is you're left with CH3 CH double bond CH2 plus H2O plus your lone pair of electrons Br minus. So yeah. Rate equations. Rate equation is rate equals Ka squared B. Draw a tangent to the curve at t is equal to 0. Okay, so just look at t is equal to 0 and just draw a tangent. Use this tangent to reduce initial rate of reaction. So let's say I stop here. We should get 0.50 divided by 11 and therefore you should get 0.05 moles per dm minus moles per dm minus cube s power minus 1 0.045. Experiment was repeated at the same temperature and with the same initial concentration B, with the greater initial concentration A. A new initial rate was 1.7 times greater than initial experiment. Calculate new initial concentration A. So what it's telling me is that same temperature, experiment was repeated, same initial concentration of B, but the new initial rate was 1.7 times greater, and it's obviously going to be due to the different initial concentration of A. So if the rate increased by 1.7 times, by 1.7, B stays the same, what's happened to A? Well, I know that therefore A is going to increase because A is squared, it's going to increase by root 1.7. And therefore to find out the new concentration of A, it's going to be the new initial concentration of A. Well, root 1.7 is what? 1.30, so it's going to be 1.30 times by 0.50, which would give me 0.65 moles per dm minus cube. Question 3, calculate value for the rate constant at this temperature and give its units. Okay, so I know in one experiment 25 degrees Celsius, initial rate is that, well, initial concentration is that, initial concentration is that, rate constant. So rate constant K equals rate divided by concentration of C times by concentration of D, which is the initial rate 3.1 times by 10 to the power minus 3 divided by 0.48 times by 0.23. And that will give me the rate constant. The units, now I'm working with moles per dm minus cube s to the power minus 1 dm cube s to the power minus 1 over mole per dm minus cube squared, because I've got two concentrations and timesing them together. Okay, well then that will cancel out and I'll be left with s to the power minus 1 over mole per dm minus cubed, which is s to the power minus 1 mole to the power minus 1 dm cubed. And for the rate constant, it is 2.8 times by 10 to the power minus 2, but that was really easy. The units, definitely slightly harder in my opinion. Question 2.3, okay, use this equation and answer from question 3.1 to calculate a value for the activation energy. So, use this equation and your answer from question 3.1, the rate constant 3.1. So I'm going to write this down. Rate constant K equals 2.8 times by 10 to the power minus 2. Now I'm going to have to rearrange it. So I'm going to times by RT. Actually, yeah, times by RT. RT. Or what I can do instead is, so I can say minus EA over RT minus EA over RT plus ln A minus ln K equals 0. Times by RT, add EA, I get EA equals RT ln A minus ln K. EA equals RT ln A minus ln K. My opinion, the rearranging of the equation is the hardest part. So I probably would have memorized it beforehand. And I'm trying to obviously find activation energy. So it's going to be RT, well, R is 8.31 times by temperature, which is obviously I want it in Kelvin, which is 25 degrees Celsius, so 298 Kelvin, bracket ln A, which is 16.9, minus ln K, 2.8 times by 10 to the power minus 6. And now if I just put that all in the calculator, ln shift ln 16.9 minus shift ln 2.8 times 10 to the power minus 2. Oh, ln A is 16.9. So I'm not doing ln 16.9. It's already 16.9. So it's going to be EA equals 8.31 times by 298 16.9 minus ln k. Okay, so that makes sense. 8.31 times by 298. Bracket 16.9 minus shift ln 2.8 times by 10 to the power minus 2. Get a ridiculously large number, but remember that's in joules. I want in kilojoules per mole to the power minus 1 divided by 1000. I get 50.7, and yeah, that should be fine, but I'll just round it to 51. Give that a UPAC name of this. So, CH3, CH2, CH2. So, first thing I would do is I can see it's a hydroxynitrile. It's got OH group and a CN group. Methane, ethane, propane, butane, pentane, hexane. So the naming of this is going to be 2-hydroxy hexane nitrile, because I've got the hydroxy group 1 and 2 on the second carbon, hydroxy hexane nitrile, 2-hydroxy hexane nitrile. Describe how you distinguish two separate samples of the two stereoisomers. Use plain polarized light. Enantiomers would rotate light in opposite directions. Use plain polarized light. Enantiomers would rotate light in opposite direction. Explain why the reaction produces a racemic mixture. Is a planar carbonyl group. It can be attacked from either side with equal probability and produces equal amounts of the enantiomers. Geological compound formed when an isomer of this, which is obviously going to be, that's an aldehyde, reacts with KCN, whereby dilute as geological compound formed just why that does not show for isomerism. So what is this mechanism? An aldehyde with KCN. Alright, yeah, obviously it's gonna be nucleophilic addition. Yeah, nucleophilic addition. But how would the mechanism go? That's what I'm trying to figure out. I'm gonna check back the textbook. Nucleophilic addition. Okay, so what's gonna happen is I've got CH3, CH2, 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 and then my CH2 C double bond O. CH double bond O. What happens is lone pair of electrons C triple bond N with negative charge attacks partially positive carbon. That's partially positive, that's partially negative. And then what happens is then this oxygen now has a lone pair of electrons and then it bonds to a H plus. So what you're going to get is CH3, CH2, 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 H, and you're also going to get COH, and then your CN group. So CH3, CH3, CH2. CH2, C, and then you got your OH group, CN group, and then you've got CH2, CH3 instead of what I said. And then why it does not show stereoisomerism, because does not contain a chiral center. CH3, CH2, COH, CN, CH2, CH3. Drug structural formula for the diester C6 H10O4. So so methane. So I'm gonna have a double bundle here, oxygen here, 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 oxygen here, 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 double bundle here, and then here. Methane, ethane, propane, butane, penthexane. Oh, actually, I know it's a diester, so it's just gonna be CH3, COO, CH2, CH2, OO, CH3. And it says complete table 1. So 0.470 minus 0.180. Well, I'm minusing 0.29, so I'm going to minus 0.29 on the other side. Sorry for the... Oh, now that is really, that's really sneaky. Because if you don't look at the actual equation, you'll get the answer wrong, because it's actually a 2-to-1 molar ratio. So I do 0.470 minus 0.180, which is 0.29, then divide it by 2, 0.145, then 0.205 minus 0.145 to get 0.06. And then for the rest, same, I'm just going to add 0.145, so 0.145, and in this case, it's just going to be 0.290. That's really sneaky. So 0.06, 0.145, 0.290. 3 marks for that. Write an expression for the equilibrium constant Kc. Remember Kc square brackets, so Kc equals square brackets of whatever the products. C6H10O4 square brackets H2O, but I've got 2 moles of it, so it's going to be squared divided by CH3COOH squared square brackets HO CH2 CH2OH HO CH2 CH2 OH. And then it says the total volume does not need to be measured to allow correct value for Kc to be calculated. Justify the statement. Well, the idea that the volumes cancel out. The volumes will cancel out, therefore it does not need to be measured. Volumes cancel out. Or you could say equal number of moles on each side of the equation. On each side of the equation, but I would just stick with of the equation. I'll just stick with the volumes cancel out. Then it says the volume of Kc was that. Calculate the amount of moles of ethanoic acid present in the equilibrium mixture. So, amount of moles of ethanoic acid. This is obviously equilibrium mole. So I'd just rearrange the equation, and basically all I'm doing is I'm swapping this out. Because if I times by both of these and then I divide by that, yeah. So it's going to be concentration of CH3COOH equals the square root of the concentration of the ester. I'll just say the ester concentration of H2O squared divided by Kc times by concentration of wherever this is, HOCH2 CH2OH. I've got Kc, that's really nice, and I've got the equilibrium moles, and I know the volumes cancel out, so all I'm doing now is substitute these values in. So square root of the ester, which is obviously is this 0.802 times by H2O squared 1.15 squared divided by Kc 6.45 times by 0.264, and then that will give me the concentrations of ethanoic acid. So if I put that in a calculator, so sometimes about the square root of that. Oh, I did a mistake in my calculator. Square root of 0.802 times by 1.15 squared divided by 6.45 divided by 0.264 and 0.789. And just one more thing I'm going to go through. You guys might be asking, Iman, isn't that concentration because it's square brackets? You're absolutely correct, it is. But remember, if you remember the equation for moles is concentration times volume, concentration times by volume, and I want to find out the moles, I've got the concentration, but I know the volumes cancel out anyway. So I don't need the volume. So therefore, moles is the concentration. George structure is zitwine formed by phenylalanine. Phenylalanine. So I need my periodic table for this. Which it should have. Guess I can go. No. Okay, let me check again. Yeah, use a data booklet to help you answer this question. There we go, got it, periodic table. And I want to look for phenylalanine. Okay, so I've got it, and it says Zwitter ion. So the number of the Zwitter ion, it's got one positively charged, one negatively charged. So, phenylalanine. So what it's going to be is, it's going to be, I'm just going to draw out phenylalanine first for you guys, and then I'm going to draw out the zwitterion for it, and how you would approach this question. Because a lot of the times, especially in paper 2, these 1 markers are the difficult questions, especially for me. So the zwitterion, well, I'm gonna have a positive charge, so we're gonna have H3N plus CH CH2. Remember, I'm not changing. The only thing I'm like making positive or negative are these side chain. This COH group and this H2N group. And this one, I need it to be negative, so it's going to be C. I'm going to have double bond over here, oxygen negatively charged. And that's it. Draw the structure of serine at high pH. Now, serine, I'm going to draw out serine again, is H2N CH COOH CH2OH H2N CHCOOH CH2OH at high pH. Well, remember, high pH, therefore I'm going to have a low concentration of H plus ions. Because opposite, if I've got high concentration H plus ions, I've got low pH, high pH, low concentration H plus ions. So if I've got a low concentration H plus ions, I want the concentration of H plus ions, right? So it's going to be H2N CH CH2OH, and it's just going to be COO minus, because then I'm going to when it's at low pH, I want the H plus to bond to it to form COOH. Draw the structures of both dipeptides form, and phenylalanine reacts with serine. Now, phenylalanine is obviously that, serine is obviously that. So what's going to happen is, I'm going to have, well, obviously this OH and then this hydrogen will leave, so I'm left with the NH and then CHCOOH, CH2OH. Or I can have it the other way around. So first thing I'm going to have it is H2N CH CH2 there we go. And then here, well, this OH leaves and this hydrogen, that's not serine, and this hydrogen leaves, so I'm left with C double bond O, and then I've got this NH group, and then I just carry on CH COOH CH2OH, and then the other one I can have is, basically what I'm gonna do is I'm just gonna is, if I've got serine here and then phenylalanine here, then what's going to happen is I'm going to have COH, sorry, HOOC, so I'm going to have So basically all I'm doing is I'm flipping it over, and instead of this group attached to CH2 here, it's just going to be there. So it's going to be HOOC, CH2, that group there, NH, CH, CH2OH, and then that goes there, NH2. An amide, alhamdulillah, an amide link is also formed when acyl chloride reacts with primary amine. Name and outline the mechanism for the reaction between methane, ethane, propanyl chloride, and a primary amine. So it's obviously going to be nucleophilic conditioned elimination. If you don't know the naming of the mechanism, I don't know how far you're going to be going and how far you're going to get to this question. So CH3, CH2, C double bond O, Cl, and I've got CH3, CH2, NH2. Remember the lone pair of electrons in this case is on the nitrogen. So remember this is partially positive, this is partially negative, this is partially negative, goes here, doop, there. Now what happens is you've got CH3, CH2, C, you've got your oxygen here, lone pair of electrons negatively charged. You've got your Cl here, and then you've got your NH2, CH3. But remember, the nitrogen now is positively charged. NH2, CH3, CH2. And now what happens is it wants to reform the double bond, so it goes here. In order to reform the double bond, the CCl bond must break. And also what happens is the Cl minus through the lone pair of electrons. But yes, that's what I memorized from the other mechanism with something else. But in this case, it's the NH2. So it's going to be the CH3, CH2, NH2, lone pair of electrons, takes a hydrogen, goes like that, and then you're left with CH3, CH2, C double bond O, and NH, CH3, CH2. CH3, CH2, C double bond O, NH, CH2, CH3, CH2, CH2, CH3. Same thing. I just need to double check one thing. Because with these mechanisms, you have to be completely correct, or you can just lose easy marks like that. The naming of it, but this is obviously going to be well, there's an ethyl group, and I've also got methanethan propane, but obviously that's name me, so it's going to be N-ethyl propanamide. Ethyl propanamide for 6 marks. N-ethyl propanamide, and you can quite easily get 5 out of 6 for this. You don't need to get 6 out of 6. Naming of the mechanisms, how well you know your mechanism, how well have you memorized it off by heart, and then this whole mechanism part, again, how well have you memorized it off by heart. This last mark, yeah, how well you can name it, N-phenol propanamide, but yeah, you should be able to get 5 out of 6 for that. Describe how you could distinguish between these test tube reactions. So K So I can see I've got two carboxylic acids. Remember, I can use sodium carbonate to test for carboxylic acid. So Na2CO3 effervescence gas slash gas turns lime water cloudy for K and M, but not for L and N. And now, what does L and N have? Well, L in N is a aldehyde, so I could use Fehling's or Tollens region. So I'll say I'll say Fehling's, and what will happen is a red precipitate, blue solution goes to brick red precipitate, N only, but not K or L or N. And then for what's it called, L, well, that's CH3CH3Br, CH2OH. So what is that? Oh, Br. So I think this is a year one. Is this year one? Let me check in textbook. So um yeah, because Br minus. So yeah, silver nitrate cream precipitate for L, but not K and N. L. Oh yeah, both L and N for L and N. So what I said for N only, and then to distinguish, so I've now distinguished between L and N. Now K and M, well, the K has a hydroxy group, and if I use acidified potassium dichromate, obviously I can use it for HO as well, but basically I use acidified potassium dichromate, acidified K2CO207, and solution turns green. Solution turns green for K and L. For K and L, because remember, K and L is both, yeah, an alkyl and aldehyde. Question 8. I can't do this part, question 8. I can do question. Okay. write an equation for the reaction of concentrated nitric acid and this. So H2SO4 plus HNO3 to form NO2 plus, and there's positive charge, plus HSO4 minus plus H2O. Yeah. Name and outline mechanism for reduction of species with nitrobenzene to form 1-13-nitrobenzene, electrophilic substitution. Electrophilic substitution. And now the mechanism for reaction of this species with nitrobenzene to form 1,3-dinitrobenzene. So nitrobenzene and the species, the NO2, and nitrogen is the one that's positively charged, here to here. Then what happens is now you've got a partial horseshoe ring. So you've got your, I want to form 1,3-dinitrobenzene. 1, 2, 3. So I put my O2 in here, and then what I have is a partial horseshoe ring, positively charged, hydrogen here, obviously, NO2 here, O2N, and then from here to here. And then what you'd form is to N, and yeah, NO2 here. 1, 2, 3, 1,3-dinitrobenzene. Because if I put it here, and then I did what I was doing, then the hydrogen, the partial horseshoe ring hydrogen here, it'd be 1, 2. Therefore, I need to move the NO2 group here. That's the only reason. 8.3 I can't do. 8.4 can't do. 8.5 can't do. 8.6 can't do. 8.7 can't do. 9.1 name the type of groups attached. X is your base, and Y is your phosphate group. X is base, Y phosphate group, and then it says complete diagram to show all the molecules and the hydrogen bonds between it and adenine. So adenine, you draw out adenine, and then so you've got, that is adenine. So between anyway, you'd have oxygen here, this here, here, nitrogen, double bond over here, hydrogen here, double bond here, CH3 here, and then that, and then hydrogen, there you go. And that would give you, because, yeah, Yeah, because you've got to spot which one it is in the DNA. I remember um, adenine to, in this case, um, thymine, I think. Question 10.1. Give the full IUPAC name of the isomer P. So first thing I would look at it is a Z isomer because it is a Z isomer because with the Z isomer on the same side, but obviously all of these four are different. So we're gonna have to look at the MR values, and if I look at the MR of hydrogen's one, MR of CH3 is 15, MR of this is what 12 plus 16 plus 16 plus 1, 45. MR of this is 12 plus 3 plus 12 plus 2, 29. So which one has a higher MR on the left hand side? This one. Which has a higher MR on the right hand side? This one. Are they on the same side? Yes, they are. So it's going to be Z dash. Got a methyl group in the second carbon. 2 dash methyl. Pent dash 2 dash ene dash 1 dash oic acid. Yeah, that's a lot for one mark. Z, because of that, what I just explained before. Methyl group in the second carbon. Pent, methane, ether, propane, butane, pentane, longest carbon chain. Pent 2E dash 1 oic acid. Then it says sample of P with mixed excess of oxygen. When this gas mixture, both gas volume measured at that. Write an equation for the combustion of P and excess of oxygen. Combustion of P and excess of oxygen. So C6H10O2 plus O2 in excess of oxygen to form CO2 plus H2O. So, and then it's just balancing it. Yeah, so you need 6 here, you need 5 here, and then you need 7.5 here. But that's for your 1 mark. Then the rest, that's going to be a bit tricky. It says, after cooling to original temperature, total volume remaining was this. This gas mixture was passed through aqueous and hydroxide, carbon dioxide, the volume of gas decreased to this. Calculate the mass of P used. Calculate the mass of P used. So I'm using PV equals NRT, and obviously in this case I need to work out the moles because I want to work out the mass of something. MR of C6H10O2, I can quite easily find that out anyway. So PV divided by RT. And so even though I'm not fully sure what I'm doing, I can still fill out the bits that I know are guaranteed that I need to do. So 25 degrees Celsius, I need to convert that to Kelvin, so 298 Kelvin. And then pressure in pascals times by volume meters cubed. Well, the pressure is the same, both gas volume measured at 105 kilopascals, 105,000 pascals. Now it's the volume I'm confused about. Which volume am I using? Am I using this volume? Am I using this volume? Am I subtracting them both? What am I going to do? So now I don't need to really worry. I can just focus on this because I've already set the footprint of what I need to do now. Just calculate volume. A sample of P mixed with excess of oxygen, mixture ignited after cooling to original temperature, total volume of gas remaining was that. When this gas mixture was passed through aqueous sodium hydroxide, carbon dioxide reacted and the volume of gas decreased to that. Calculate the mass of P used. So this is again, I'm not sure. Well, gas mixture, carbon dioxide reacted, volume of gas decreased to that. Oh, right, okay. So I need to do 335 minus 155, and then that will give me the volume of for P. So 180. But remember, I want it meters cubed, so divide by million, times by 10 to the power minus 6. Everything else is perfectly fine. I get the moles as 7.632 times by 10 to the power minus 3. But I don't want the moles. I want, actually, no, before I even carry on, that's the moles, therefore the moles of P, C6H10O2 use. Well, if I look at the equation, it's a 1 to 6 mole ratio. So if I work out the moles, I'm working out the moles of the gas, right? I'm not working out the moles of P, because P is not a gas, it's sample of P, yeah. So that would give me the moles of the carbon dioxide. Therefore, I need to divide that by 6. That will give me the moles of P, no, 1.272 times by 10 to the power minus 3. Then I can work out the mass by doing that. Moles is mass over mR. Mass is the moles times by the mR, 114. Then that will give me 100 and, wait, 1.272 times by 10 to the power minus 3 times by 114. That will give me 0.145 grams, but I want it in milligrams. So I need to times by 1000, and I get 145 grams. So this is really tricky PV because NRT question. I do gas equation question. First things first, write down the equation. PV because NRT, rearrange it, and is PV divided by RT. Put your units in, convert it, and realize the volume is just going to be this minus this, times by 10 to the power minus 6. You get the number of moles, but remember it's a 1 to 6 mole ratio, divide that by 6. Then you can work out the mass. Moles is mass over ml. Mass is going to be the mole times by ml, but that's more mass in grams. I want the mass in milligrams, so then I times it by 1000 to get 145 milligrams. 10.3 I can't do. 10.4 can't do. 10.5 can't do. 10.6. Maybe I can do that one. It says 5-hydroxyhexanoic acid loses two different products. Loses water to form a second compound. It forms a polyacid or a structure of T. Nah, I probably can do that, but I'm going to leave that one out because all of these are, I guess, somewhat the thing. Question 11. Question about the three amines, E, F, and G. Explain the difference in base strengths of the three amines and give the order of increasing base strength. Before I even start, typing away, which one is going to have the highest base strength? Well, it's all about the nitrogen, really, and it's going to be F is definitely going to have the highest because with E and G, the phenyl group, with the delocalized lone pairs, they're going to be delocalized into the ring. But with F, it's not attached to the benzene ring. It's attached to CH3, CH2, which is attached to the benzene ring. So F is definitely going to have the highest. And E and G, well then, whereas with G, I've also got two alcohol groups attached to it, so that's going to be second and that's going to be third. Now we can start typing away. So, first thing I would say is strength depends on availability of lone pair on nitrogen atom. E and N are next to the ring, hence lone pair delocalize into the ring. And I remember strength depends on availability of lone pair nitrogen atom. Lone pair less available to donate slash to accept a H plus. F or G or both of them are next to alkyl slash positive inductive effect. Electrons are pushed onto N, or pushed to N. Lone pair is more available to donate slash accept a H plus, and therefore order of increasing base strengths. So I'm going to do lowest, the weakest base strength to the highest. But I know the weakest is E because the nitrogen is directly attached to the. Lone pair can be delocalized into ring, plus it's not got those positive inductive, the alkyl groups, the electrons pushed to N, it's not got that, so it's going to be E. Then it's going to be G, and then it's going to be F. Then it says amine F can be prepared in 3-step synthesis starting from methylbenzene. Methylbenzene. Okay, methylbenzene. And I want to go from methylbenzene to an amine F. To this. So first thing that's going to happen is the two structures. Well, I'm going to have C6H5. I want to go from methylbenzene to just amine. So C6H5CH2 Cl, then C6H5CH2 Cn, and then you can get your amine. So C6H5CH2 Cl, C6H5CH2 Cn. Step 1, chlorine and UV light, because that's all I've done really. And step 2, KCN, alcoholic, and aqueous. Remember, that's just going to be nucleophilic substitution. So the first one, free radical substitution. Next one, nucleophilic substitution. Step 3, well then to get to your amine, nitriles can be reduced to amine. So then I'm going to use hydrogen slash nickel, or PT or PD, and this is obviously catalytic hydrogenation. So C6H5CH2Cl and C6H5CH2Cn. So it's very simple. C6H5CH2Cl, C6H5CH2Cn. Step 1, chlorine and UV light. Step 2, KCN aqueous, alcoholic and aqueous. Step 3, catalytic hydrogenation, hydrogen and nickel catalyst. And again, how well you know your reagents, conditions, your pathways, 5 marks. And there you go. And that is the end of the paper.